Hi guys, today we're going to start chapter 7, which is balancing equations, stoichiometry, limiting and excess reactants, and then a little bit about types of equations. So before we do anything, I do want to let you know that I did post a practice, which is completely optional. However, if you are not good at balancing equations, you're going to need to probably do it because if you can't balance equations, you're kind of out of luck for the rest of the semester. Okay, and if you need help, I really need you to reach out and let me know via Remind, via email, come to office hours, something, okay? All right, so we use types of reactions and stoichiometry and things like greenhouse gases and how it's affecting the atmosphere. It's very common that we use this in real world situations because we need to know how much our gas is converting to those greenhouse gases. Our gas for the cars is using the gasoline up and then converting to carbon dioxide and water and then harming our environment potentially. Okay, and here's just some graphs of how global warming has affected us temperature-wise. First, we're going to talk about physical and chemical changes, which hopefully you already understand. Just remember that a physical change is a state change. So it's a change that alters the state or the appearance, but not the composition, so not what's on the inside. So here you can see liquid water in this image kind of in the middle on the right. And at the top you see gaseous water. And notice there's lots more space between them. This is a physical change. I do want you to know sometimes people say that bubbles are an indicator of a chemical change, which is true, but these bubbles are caused by the heat that we're putting into it. So that's not particularly a chemical change. Okay, but the big thing is it does not change the identity of a substance. What's on the inside of it is still the same. Chemical changes, on the other hand, do alter that composition of the matter. So here we've got pure iron in that top right picture. And on the bottom, when it starts to oxidize or rust, there's little oxygen particles in there. And that's one of the things that causes it to change color because now it's a new substance. It's iron 3 oxide instead of just pure iron. So, which change is a chemical change? The evaporation of rubbing alcohol, and the word evaporation means state change, so that's physical. The burning of lamp oil, or the forming of frost on a cold night. So, frost is from gas in the air to solid. So, our chemical change is going to be burning. Also, another way to think of it is, can I get it back without doing another chemical change? So, once I've burned that oil, I'm not going to be able to get it back. It's gone. If I form frost on a car, if I heated it back up, it would turn back into a gas state. Okay, 7.2. The diagram on the right shows liquid water particles. Which of the three diagrams best represents the water molecules after they've been vaporized, which means physical change because it's going to gas? That one's going to be A. A lot of times my students will choose B or C when we're in a classroom. And I completely understand that, yeah, it's going to a gas, so those are valid, quote-unquote, options. However, remember, physical changes keep the molecule as it is. Okay, so the water molecule is intact in the liquid, and it's intact in choice A. All right, so some things to keep in mind for chemical reactions. We've got reactants on the left, an arrow, and then products. Okay, the reactants will always be on the left, there will always be an arrow, and there will always be products on the right. These are states of matter, and we're going to start seeing those. So just know that G is for gas, L is for liquid, AQ means aqueous, which we'll talk about, but that just means dissolved in water. And then S is for solid. And there they are in the picture. I didn't know they were going to show up on the next slide. I knew they were in this PowerPoint, but I thought they were a little farther away. Okay, so when we're balancing equations, it's very important that you make sure the elements on the right equal the elements on the left because the law of conservation of mass states that you cannot create or destroy matter or mass. Okay, so this equation is balanced, and we're going to learn how to balance them. Stoichiometry is the reason we balance them, and that'll be the next video, and that uses numbers with moles. So we'll get to that in the next video. This one, balancing equations. Write a balanced equation for solid cobalt-3 oxide and solid carbon. It produces solid cobalt and carbon dioxide gas. Okay, so it's very important, one, that we have our periodic table out here, and two, you know your naming rules. Because if you don't know your naming rules at this point, you're also in trouble. So again, if you need naming practice, please reach out. I can get you some. Okay, so cobalt oxide, it's cobalt-3 because it crosses over. Oxygen's charge is 2. It tells me it's solid. Also, make sure you're leaving space in front of each compound or element so we can put a coefficient if we need to. Produces solid cobalt and carbon dioxide gas. Also, really make sure your small O's and your big O's look different because there's cobalt and oxygen and just regular carbon, so that could get a little confusing. Okay, if you've never balanced an equation before, the best thing to do is account for what you have currently on both sides of your reaction. And this reaction I currently have is called a skeletal equation because I don't have any coefficients. It's not balanced. So on the reactant side, I've got 2 cobalts. On the product side, I have 1. On the reactant side for oxygen, I have 3. Products, I have 2. Carbon, I have 1 and 1. Okay, the only rule I have for now is that we normally leave the nonmetals till the end because often they're in more things. Okay, so let's start with our metals. So, cobalt is not balanced. If I times cobalt by 2, it will equal 2. So I'm going to go ahead and put a 2 there. Carbon is good. Oxygen is my next problem. Oxygen is 3 and 2, and I can only add coefficients. I cannot change subscripts. Subscripts are the little numbers. Coefficients are the big numbers. Okay, so that means I have to do something to both of them to make them equal, and it's going to be to make them equal to 6. Okay, it is very important that notice I'm multiplying this oxygen by 2. I have to multiply that whole compound by 2. When I do that, that messes with this number. It becomes 4 because coefficients distribute their numbers. Okay, so now I don't have 2 cobalts on the reactant side. I have 4. And now I do not have 1 carbon on the product side. I have 3. It is important to know that whatever number you multiply them by is the number that goes in front of the compound that that element is in. Okay, now, most of you will not need to do this every time, but some of you will. And again, if you need extra help, please reach out. Okay, I've got tons and tons of stuff for balancing equations. But if you don't reach out, I don't know you need help. And this is our first chapter on our new topic. So luckily, this is going to bleed into our week 4. So the test for that one won't be until week 4. But we are looking at, if you don't get it early on, it's going to mess with everything else. Okay. Okay, we've got another one. Silicon dioxide. So this one I'm going to do a little bit different. I'm going to keep track of them, not on paper, but I'm going to keep track of them verbally. So in my head, if I were doing it by myself. Produce solid silicon carbide plus carbon monoxide. Okay, I will also tell you, mastering chemistry is going to be very particular that if it says states of matter, you put them. So make sure you're on board with that. Okay, I've got 1 silicon on the left, 1 silicon on the right. 2 oxygens on the left, 2 carbons on the right. Sorry, 1 oxygen. So my oxygen's off. I'm going to put a 2 here. That fixes my oxygen. Now I have 1 carbon on the reactants, 3 on the, because you have to add them if they're on the same side. There's a plus sign there. So I'm going to put a 3 here, and that one solves my problem. So some of you can do it this way. Some of you need the other way. Also remember, I posted those book videos, and I promise there's one doing balancing reactions, okay? All right, combustion reactions. C4H10, and that's a gas. It says gaseous butane, plus combines with oxygen. Sorry. To form means arrow, gaseous carbon dioxide, and gaseous water. Okay, it is very important. So first off, this is a combustion reaction. It even says that, and this is coming later on in part 3 of this chapter, but it says combustion here, so that means this is a specific type of reaction, which I'm going to continually refer to. So all combustion reactions for now in this class are going to produce carbon dioxide and water in gas form, and they will all have oxygen as part of their fuel to burn, because you can't have fire without oxygen. Kind of like candles. If you cover a candle and cut off its oxygen supply, it's going to blow out. So then you don't have any more fire. Okay. The rest of it is some hydrocarbon, which is just carbons and hydrogens together, which we did talk about in chapter 4. All right. Now we need to balance. 4 carbons, so I need 4 carbons. 10 hydrogens. I've got 2 on this side, multiply by 5. 2 oxygens. On the product side, I have 8 plus 5. That is 13. I cannot make, the only way to make this 13 is to do 13 halves, which we cannot do that because coefficients must be whole numbers. So I start over. And I'm just going to multiply everything by 2. The best thing I can tell you, that should be 8 now, is to start all combustion reactions with a 2 in front, and then if it's easier to reduce at the end than it is to do it again. Okay, so this one is the answer, not the top one, because you cannot have fraction coefficients. Okay, one more. Combustion again. I've got ethane plus oxygen gas yields carbon dioxide and water. Again, I'm going to focus on putting a 2 here in front just to make it easier. So now I have 4 carbons, and now I have 12 hydrogens. So 2 oxygens, I've got 8 and 6. 8 and 6 is 14, so this must be a 7. Okay. Again, if you need help, please let me know. If all of your coefficients are divisible by the same number, so let's say they're all even, you do need to go ahead and reduce it, but we haven't had any come out like that. All right, one's with polyatomics. So I've got strontium chloride. Don't forget about your charge for strontium. Lithium phosphate. Don't forget about phosphate's charge. Check your polyatomic chart if you need to make solid strontium phosphate. And lithium chloride, aqueous. All right. Okay, yes, all my charges are good. So at this point, this is the first time we've seen polyatomics. If there are polyatomics on both sides of the arrow and they are together, we're counting them as a whole thing. So I'm going to count both of these as one whole thing. So let's start with strontium. Got 1 strontium on the reactants, 3 on the product. So I'm going to put a 3 there. 6 chlorines now, so I need a 6 here. 3 lithiums, but I've got 6 on the product, so I need a 2 there. And now I have 2 phosphates and 2 phosphates. So this one is done. I think we have one more example. There we go. Lead to nitrate. So PbNO3 2. Don't forget, polyatomics need to go in parentheses if they have a number outside of them. Ooh, I wrote L. I don't know why. PbCl2 solid plus KNO3. Aqueous. Don't forget, gotta have your states of matter for mastering chemistry especially. So my lead is okay on both sides. Nitrate, I've got 2 nitrates, but only 1 on the product. So I'm going to put a 2 in front. 1 potassium and 2 in the product. So I put a 2 there, and now I've got 2 chlorines, 2 chlorines. Okay, this is where we're going to stop for today because I need you to make sure you can balance equations. Please let me know if y'all need more help. Y'all have a great day.